Swayam Prabha. Digital India. Educated India.
So let me have your attention. See, we have to prove the two things. You have to prove two things. One is the injectivity and then the surjectivity of the classification map. Okay. Recall that there is a classification map that attaches to every unit speed curve its curvature and torsion. Okay, and you take all the curves and you go modulo this equivalence relation given by rigid motions. So the map is actually from the rigid motion equivalence classes of unit speed curves to pairs of functions, the first member of the pair being the curvature, the second member being the torsion. Okay. Now to show the injectivity of this map, we have to prove, as I've already told you, we have to do the following thing. You have to take two curves, capital gamma 1, capital gamma 2, okay, and you assume that the curvature of gamma 1 and the curvature of gamma 2 are the same, and similarly the torsion of gamma 1 and the torsion of gamma 2 are the same. Okay, then you have to show that gamma 1 can be moved to gamma 2 by a rigid motion. Okay, so basically these two pairs being equal should imply that these equivalence classes are the same. Okay, that's what we have to prove. That is injectivity of this map. Okay, so basically you start with these two curves, capital gamma 1 and capital gamma 2, which have the same curvature and torsion, and you have to find the rigid motion. Okay, now this is the way to do this is you can use both a little bit of the theory of uniqueness of solutions of differential equations, as well as even indirectly you can use that, or directly you can just use the Frenet-Serret relations. Okay, there are two ways of showing this. So let us think about this. So you see, you have, so here is my curve. So here is my curve gamma 1, right? Mind you, gamma 1 is gamma 1 of S. So gamma 1 is a function from AB into R3. Okay, and this is gamma 1 S is unit speed parameterized, and therefore S is increasing arc length. Okay, so gamma 1S is a unit speed parameterized curve. S is increasing arc length. And what are the assumptions? You see, the assumption is the k gamma 1 of S is positive. Okay, so it has positive curvature, right? Mind you, this is a space curve, curvature is not signed, so curvature only means magnitude of the curvature. Okay, and we take it to be positive, right? It should never vanish. Why the curvature should never vanish is because we want torsion to be defined. Torsion is defined only when the curvature never vanishes. So the curvature is positive, and then what happens is that this is associated to curvature function k gamma 1s and tau gamma 1s is the corresponding torsion function. So you have this pair, right? Now suppose we have some other curve gamma 2 of S, again of a similar type. By the way, I should also say that curvature is for the curvature to make sense, curvature is essentially the second derivative in a normalized sense, so it should be second continuously differentiable, and the torsion involves the third derivative, and therefore the curve has to be third continuously differentiable. Therefore it's important that gamma 1 here is in C3AB. So similarly I have another curve gamma 2. So gamma 2 now is again from the same AB into R3 is another space curve, and again gamma 2s is unit speed parameterized, and where s is increasing arc length. Okay, and again the curvature of gamma 2 is positive always, so that the torsion is defined, and then you associate to this curve its curvature and torsion. So k gamma 2s comma tau gamma 2s. Okay, these are the respectively the curvature and the torsion for gamma 2, and again gamma 2 is also third continuously differentiable on AB. Okay, you need that for the torsion to be continuous. Okay, so since the curvature is the second derivative, okay, I mean it involves the second derivative, it is the magnitude of the second derivative, all right, but this is third continuously differentiable, therefore the second derivative is first continuously differentiable, and therefore the point is that the curvature is C1. Okay, so this first member is C1, the second member is C0. Okay, and the first member is C1 with values in R plus, okay, real positive real value. The second one is torsion, it's continuous, and its torsion can be any sign, it can be positive or negative, it can be 0. All right. Okay, now what is given is that these two curves have the same curvature and torsion functions, and the claim is that there exists a rigid motion that moves gamma 1 to gamma 2. Okay, so given k gamma 1s is equal to k gamma 2s and tau gamma 1s is equal to tau gamma 2 of s. Okay, to show what do you have to show? You have to show there exists a rigid motion m from R3 to R3 such that m takes gamma 1 to gamma 2. So m circle gamma 1 is gamma 2. Okay, and this is the same as saying the equivalence class of gamma 1 is the same as the equivalence class of gamma 2, where this square bracket means rigid motion equivalence class. Okay, gamma 1 is rigid motion equivalent to gamma 2. Okay, so this is what you want to prove. Now, therefore, what is the issue? The issue is that you have to find a rigid motion. All right. Now, how do you find that rigid motion? Just assume it existed and see what happens. See, so here is so let me draw a picture like this. So here is my AB, okay, and my gamma 1 is a map like this. Okay, and this gamma 1 is might be sitting inside R3, and then this gamma 2 is also sitting inside R3. Okay, and capital gamma 2 is thought of as a map like this. Okay, and of course I am confusing the map with the parameterization with also the curve that it traces. Okay, but you understand what is being meant. All right. So now suppose, so what you want is you want to show there exists an m rigid motion which takes gamma 1 to gamma 2. This is what you want to show. Okay, you have to show such a rigid motion exists. See, suppose such a rigid motion existed, okay, then what does it mean? You see, let us take any point S0 in AB. Okay, what will happen is this S0 will be taken by gamma 1 to a point gamma 1 of S0. So there is going to be a point on the first curve. Okay, then the same S0 will go to some point here. It will be gamma 2 of S0. That's on the second curve. Okay, now if there is a rigid motion that is moving gamma 1 to gamma 2, then that rigid motion m has to take this gamma 1 S0 to gamma 2 S0. Right. So therefore, what happens is that this will go to this. gamma 1 S naught, m circle gamma 1 of S naught will be equal to gamma 2 of S naught. This will happen. If there is a rigid motion, this has to happen. Okay. And what is simple rigid motion that will move this point to that point? A translation. Okay. Okay. You are trying. See, mind you, this is an intuitive way to get hold of a rigid motion. And you know, generally every rigid motion can be written as a rotation, that is a linear isometry for an oriented rotation, that is an oriented linear isometry followed by a translation, or the other way around. You can first write it as a translation followed by a oriented rotation, oriented linear isometry. Okay, so we are trying to guess to get hold of this m, to guess this m, you have to guess its translational component and you have to guess its rotational component, and that's what we are trying to do. So you see, the translational component is very, very clear. See, if there is a rigid motion that takes gamma 1 to gamma 2, it will translate gamma 1 S naught to gamma 2 S naught, and therefore the translational component has to be this. So you see, this component, so you can take T V, okay, I'll just call it as T V, which is, you know, T of gamma 2 S naught minus gamma 1 of S naught. Okay, where your V, so let me write, I call it as V naught if you want, where, you know, V naught is just gamma 2 S naught minus gamma 1 of S naught. So I can take this translation. Okay, what this translation will do is that it will move this whole curve will be moved, the whole curve gamma 1 will be moved to another curve. Okay, now that curve and this gamma 2 will intersect at the point corresponding to S naught. So what will happen is that, you see, suppose, so let me use a different color for that. So let us say I use blue. So you see, I have this curve, I apply this translation. I apply this translation, this is TV naught. Okay. If I apply this translation, what will happen? See, what does translation do? It moves the curve, you know, so that at every point, if you want, the Frenet-Serret frame is only moved translationally. The new curve at every point will have the Frenet-Serret frame parallel to the Frenet-Serret frame of the original curve. Okay. The translation does not do anything else. Okay, so if I move this curve, what will happen is that I will get something like this. So let me draw this. I will get like this. So this will be, first apply gamma 1 and then gamma 1 and then apply m TV naught. This will be this curve. Okay, and of course let me put an orientation. So this is so I even there let me put the orientation there. So here it is like this, and here also it is like this, and in this moved curve it is like this. Okay, so I have this translation now, right? Now what else? So you see this blue curve, which is TV circle gamma 1 and gamma 1, they are actually parallel to each other in the sense that at every point, you see, they only differ by a translation. All right. Now, what does this translation do? Mind you, translation is also a rigid motion. Okay, and it will, and you know, when you apply a rigid motion, curvature and torsion will not change. That is something we have already proved. Okay, when you take a curve and move it by a rigid motion, then the curvature and the torsion do not change, and that is the reason why, you know, the curvature and torsion don't depend only on the curve. They depend only on the rigid motion equivalence class of the curve, and that's why you are able to get a function, curvature function and torsion function defined on the whole rigid motion equivalence class. Okay, therefore you see, when I apply this translation, this new blue colored curve TV naught circle gamma 1, that will still have the same, you know, curvature and torsion functions as gamma 1. But curvature and torsion functions of gamma 1 are supposed to be the same as curvature and torsion functions of gamma 2. Therefore, this T V naught circle gamma 1 and gamma 2, they both have the same curvature and torsion functions. Okay. So, what has happened is that now you have moved gamma 1 to intersect gamma 2 at a common point. By common point, I mean it's a point corresponding to a single parameter. Okay, right? That parameter value is S naught. But now what you have to do is that you see, look at the Frenet-Serret frame. Okay, look at the Frenet-Serret frame. Under translation, the Frenet-Serret frame is just translated parallel to itself. Okay, so look at the Frenet-Serret frame at gamma 1 S naught. So what is going to happen is, so let me draw another picture. So you see, you are going to have something like this. So at gamma 1 S naught, I am going to get a frame here. This is n gamma 1 cap, and then the binormal b gamma 1 cap. Okay, I get this orthonormal frame. Okay, this is the Frenet-Serret frame of gamma 1. Okay, and this point is so let me draw this. This point is this is gamma 1 of S naught. Okay, and therefore, if you want, this is n gamma 1 at S naught, this is b gamma 1 at S naught, and this is t gamma 1 at S naught. So I get this Frenet-Serret frame here. Mind you, this is perpendicular to this is perpendicular to this, and these two guys are also perpendicular. Okay, it's a right-handed orthonormal frame. Now what has happened? You have applied this this translation TV naught. So this orthonormal frame will just go and get translated, and by the same TV naught, and I'll get an orthonormal frame for the translated curve. So what I'll get is, I'll get something here. So here I will draw the same thing here. So for this curve also, I will get again, let me rub this. Oops. So again here I am going to get, you see, oops. So again here I'm going to get T. So I'm going to get T cap TV naught circle gamma 1 of S naught. Mind you, this point is gamma 1 of S naught, and that is also equal to gamma 2 of S naught. I should write T V naught circle gamma 1 of S naught, and that is gamma 2 of S naught. Okay, right? And at that point, I am going to get the Frenet-Serret frame of T V naught circle gamma 1 S naught. Mind you, this is the same as the Frenet-Serret frame of gamma 1, because the difference is only a translation. So this guy is the same as the Frenet-Serret, second member of the Frenet-Serret frame for gamma 1. So I will just write it as n cap gamma 1 of S naught, and this guy here, T V naught circle gamma 1 S naught, will be the same as b cap of gamma 1 of S naught. Okay, so this is the Frenet-Serret frame I get for the translated curve. Okay. On the other hand, gamma 2 itself has a Frenet-Serret frame at that point. Okay. So let's draw that also. So let me say things again. Okay. See, first you have this red curve on the left side, which is capital gamma 1s. Okay. It passes through this point capital gamma 1 of S naught, which has this purple Frenet-Serret frame, right? Now then you have this other curve, which is the light blue curve, all right, which is gamma 2 of S. That there is this point gamma 2 of S naught through which it passes. Okay, I take the same S naught parameter value for both curves. Okay, I get a point on the red curve and I get a point on this light blue curve, right? Now this gamma 2 of S at gamma 2 at S equal to S naught, namely this point gamma 2 of S naught, okay, you again have this light blue orthonormal frame that consists of the the T cap, the N cap and the B cap for gamma 2. Okay, so this is supposed to be 2 here. Okay, right. Now what I am doing is that I am taking this point gamma 1 S naught and I am moving it to the point gamma 2 S naught, right, by this translation TV naught. After I move it, you see this red curve which is gamma 1 of S, okay, that becomes this blue curve, this dark blue curve which is TV1 circle gamma 1 of S is just a parallel translate. And under this parallel translation, the Frenet-Serret frame of gamma 1, which is in purple, goes to the Frenet-Serret frame of TV circle gamma 1. It is just a parallel translation. Okay, so what will happen is that I will get this purple frame here. Okay, and mind you, the frame vectors have not changed. So the Frenet-Serret frame of TV0 circle gamma 1 and that of gamma 1 are the same, right? On the other hand, gamma 2 has its light blue Frenet-Serret frame there, okay, at gamma 2 S naught. Now you see, just look at the point gamma 2 S naught. There are two Frenet-Serret frames, there are two orthonormal frames. There is this purple one which is translated from the orthonormal frame of the first curve, okay, and there is this light blue one which is the orthonormal frame of the second curve. They are two different orthonormal frames for these two different curves which pass through the same point for the same parameter value, alright. But here is a beautiful thing, any two orthonormal frames you can always move one to the other by an orthogonal transformation, okay. That is something that I have already told you. In fact, any two orthonormal set of vectors, okay, you can always if you take any two ordered orthonormal sets of vectors, you can always find an orthogonal transformation that moves this to that, okay. And the method is that you write it as a matrix and you use linear maps, okay. That is something that we have already seen. So in fact, if you want, I can recall that. So you see, let me recall this. See, suppose you have an ordered orthonormal basis V1 through Vn, okay, and you have another ordered orthonormal basis W1 to Wn, okay. There is a linear isometry that takes this orthonormal basis to that orthonormal basis. And what is it? It's very, very simple. You take this first orthonormal basis, put it as a matrix, okay. Then that matrix is an orthogonal transformation. And what is the transformation? The transformation is the transformation L sub A, which maps the EI to the VI for every I by the definition of a matrix of a linear map. Similarly, this other orthonormal basis W1 through Wn, you construct a matrix out of that by just putting those vectors as column vectors. You will get another orthogonal matrix. And the linear map defined by that is the unique linear map that takes EI to WI. Okay. Now, how do you get this map L? Basically, what you have to do is you have to go this way and then go like this. That means you have to go by LA inverse and then you have to apply LB. So it's first apply LA inverse, then apply LB. But you see, LA inverse, the matrix of LA inverse is just A inverse. So it is the same as first applying A inverse and then B and taking the linear transformation corresponding to that. Therefore, the BA inverse is the map that will take V1 etc. Vn to W1 etc. Wn. Okay. So this was the proof that any ordered orthonormal set of vectors can be moved to any other ordered orthonormal set of vectors by an orthogonal transformation. Okay. So in this case, we are having two Frenet-Serret frames, and you want to move one to the other, right? You want to move the one orthonormal frame to the other. There is an orthogonal transformation that will move it because of this generality. But there is one catch. A general orthogonal transformation may either preserve or it will reverse the orientation. But if it is if it is going to take a right-handed frame to a right-handed frame, then it has to preserve orientation. If it reverses orientation, it will change the handedness. Okay. So what is happening is that, you see, in our situation, the current situation, if you look at it, we have two right-handed frames. Okay. So there is this this purple frame here is a right-handed orthonormal frame by definition for the red curve gamma 1. Then by translating it, I get this I get this purple frame here. Where is that? I get this purple frame here, this one here. That is just a translate of a right-handed frame, so it's also a right-handed frame. Okay, and then there is also this light blue frame, light blue colored one, which is the orthonormal frame of gamma 2 at S naught. That is also right-handed by definition. Remember, the Frenet-Serret frames are all right-handed by definition, because what you do is you first write the tangent vector, unit tangent vector t cap, then you write the principal normal n cap, and the b cap is defined in such a way that it is t cap cross n cap. So therefore t cap, n cap, b cap is automatically a right-handed frame. So therefore this purple right-handed orthonormal frame can be moved to this light blue right-handed orthonormal frame by an orthogonal transformation, and since both of them are right-handed, this orthogonal transformation has to be orientation preserving. Okay, so what I can do is, basically I can apply that that will be a rotation. It's a generalized rotation that will I can apply that rotation to this blue curve. If I apply this rotation to this blue curve, I will get another curve. Mind you, that rotation is for that rotation the intersection point is fixed, because it is considered as a rotation about that point. Okay, so what will happen is this blue curve will get moved to another curve. Now this new curve that you get after the rotation, the Frenet-Serret, the purple Frenet-Serret frame will go and superimpose on the light blue Frenet-Serret frame because of that rotation. Okay, now here is the point. What has happened is, this blue curve goes to another curve, and that curve and the light blue curve, they have the same, they pass through the same parameter point with the same parameter value, and at that point they both have the same, only at that point they have the same Frenet-Serret frame. Okay, now here is the beautiful thing. If that happens, they will have the same Frenet-Serret frame everywhere, and they have to be one and the same curve. That's the whole point. Okay, and so let me repeat it. There is this blue curve. It has this purple orthonormal frame at that point of intersection, which is gamma 2 of S naught, and the light blue curve also has a light blue colored orthonormal frame. Both of them are right-handed. There is an orthogonal transformation that takes this to that. It will be an orientation preserving transformation. Apply the transformation to the whole blue curve, I will get a new curve. That curve and the light blue curve, they both pass through the same point for that parameter value, and at that point their Frenet-Serret frames are going to be one and the same. Okay, but now look at this. Both of these curves will be solutions to the same Frenet-Serret differential equation with the same initial conditions. Namely, it's a first order differential equation. Okay, and the initial condition must be, I have to give you a point, and I have to give you the tangent, the normal and the binormal at that point, but that you have already specified. Therefore, they have to be one and the same curve. So the moral of the story is that if you take the unique rotation that will move the the purple orthonormal frame to the light blue orthonormal frame and apply it to the blue curve, you will get the light blue curve, and you're done. Therefore, the rigid motion will be, first do this translation by V naught, then follow it by this rotation. That's all. So you have found a rigid motion. Okay. So So here you are using the fact that there is a uniqueness to the solutions of a first order linear differential equation given initial conditions, the same initial conditions. Okay. So let me write this down. So let me write the following thing. I'll just say take S naught belonging to AB. Okay. Take TV naught is equal to translation by V naught, where V naught is gamma gamma 2 of S naught minus gamma 1 of S naught. Okay. Then TV naught circle gamma 1 of S naught is TV naught of gamma 1 of S naught, and that will be gamma 1 of S naught plus V naught. It is gamma 1 S naught plus gamma 2 S naught minus gamma 1 of S naught, and that is going to give me gamma 2 of S naught. Okay. Also the curve TV naught circle gamma 1 is a translate of gamma 1, so it has the same curvature and torsion and Frenet-Serret frame as gamma 1 at S naught. Okay. So so let me write this. So K TV naught circle gamma 1 of S is equal to K gamma 1 of S and then tau TV naught circle gamma 1 of S is equal to tau gamma 1 of S. Okay. And this is for all S in AB. Okay. That's because if you apply a translation, or for that matter any rigid motion, the curvature and torsion functions will not change. So this is valid at every S. But at S naught, what happens? You see, at S naught the Frenet-Serret frames. So I can also write. So I want to write the following thing: T cap. I can also write it for all at every point for the even for the Frenet-Serret frame. So I can write T cap of TV naught circle gamma 1 of S naught is equal to T cap of gamma 1 of S naught N cap and similarly for B cap. Okay. So you have the Frenet-Serret frames are the same, right? You see the curve is moved by rigid motion. Okay. But you see this rigid motion is only a translation. Okay. So when you put a dot on the curve to get the tangent, the translation vector, the derivative of the translation vector will become 0. So at the at the level of the Frenet-Serret frame, it's going to everything is going to be the same, which is d by ds at S is equal to S naught of TV naught circle gamma 1 of S. Okay, and that is going to be d by ds at S is equal to S naught. I should write this is gamma 1 S plus V naught, okay, and this will give me, oops, this, they really made a mess of this thing, and this is going to give me, and now there is this constant here, so I will get d by ds at s is equal to s naught of gamma 1 of s, that is gamma 1 dot of s naught, and that is t hat gamma 1 at s naught, okay, right. So one has to similarly write out expressions for n cap and b cap, okay. I will exempt myself from writing this down, all right. So essentially, and okay, if you write it for n cap, you will have to use the first Frenet-Serret equation and use the fact that after translation, the curvature function does not change. So if you want for this n hat of, so let me write it so that you know, this is by definition 1 by curvature of t v naught circle gamma 1 at s naught into the t dot t cap dot of t v naught circle gamma 1 at x naught. This is by the first Frenet-Serret equation, but you see, yeah, the curvature is the same as the original curve because you are moving it only by translation, which is a rigid motion. So it is 1 by k gamma 1 at s naught, and see already the tangent vectors are the same, therefore the derivatives are the same. So I will get this also as t cap dot gamma 1 at s naught, okay. So you will get this, and then once you get this, the third one will also follow. If the t's and the n's are the same, then the b's are the same because the b is given by t cross n, okay. And so therefore what I want to say is that so I'll just write it here. This is, see, I'll just say valid not only for s equal to s naught, but you know, for all s, okay. So here I don't have to really be obsessed about s naught. It's only I have to be obsessed about s naught only when I try to compare this translated curve t v naught circle gamma 1 with gamma 2. That's where the issue actually comes. So what I want to say is for t v naught circle gamma 1 and gamma 2 of s, okay, we have the same, you know, the same curvature and the torsion functions. See t v naught circle gamma 1 and gamma 1, they differ only by a translation. So they have the same you know, curvature torsion, but already gamma 1 and gamma 2 are assumed to have the same curvature and torsion. Therefore t v naught circle gamma 1 and gamma 2 also have the same curvature and torsion, all right. So they will still have the same curvature and torsion. The only problem is that the Frenet-Serret frames, the curves don't, as it is superimpose, they pass through the same point for the parameter value s naught, and at that, even at that point, you see the Frenet-Serret frames are different, okay. So let me write this k. So I'll just write it like this: curvature of t v naught circle gamma 1 of s is the same as curvature of gamma 1 of s is the same as curvature of gamma 2 of s. This is by hypothesis, okay. And torsion t v naught circle gamma 1 of s is equal to torsion gamma 1 of s is equal to torsion gamma 2 of s. This is for all s in AB, okay. They have now the thing is that look at the Frenet-Serret frames at that intersection point. We have, you know, t cap, it's you know, so the Frenet-Serret frames this is the same as t cap t gamma 1 as, of s naught and n cap and B cap okay. We have this, this is the FS frame for TV naught circle gamma 1 at S naught, and then there's this other one that corresponds to the Frenet-Serret frame for gamma 2 at S naught. So I'll have T cap gamma 2 S naught, N cap gamma 2 S naught, B cap gamma 2 S naught. This is the Frenet-Serret frame for the second curve. Okay. Now both of these are two Frenet-Serret frames at the same point. Okay, and you can use rotation at that point. You can use an orthogonal rotation at that point. Okay, to move one frame to the other. Okay, so there is a rotation that I can do. All right, let G be the oriented linear isometry oriented rotation that moves the Frenet-Serret frame for TV naught circle gamma 1 at S naught to the Frenet-Serret frame for gamma 2 at S naught. Okay. Now I want, what I should apply to the curve is I want to apply this rotation to the curve in such a way that the point is fixed. Okay. The confusion is that the Frenet-Serret frame at a point, okay, when you just look at the frame as frame vectors, it's actually the Frenet-Serret frame is based at the origin, but we draw it at the point on the curve. Okay, and if you have two Frenet-Serret frames, two orthonormal frames at a point, and thinking of that point as fixed, you have a rotation that moves this to that, but that point is not necessarily the origin. Okay, so the way to write it is that you think of these two frames based at the origin. There is a honest rotation. It's a linear isometry. Okay, and how you act it on the curve is that you have to first translate that point to the origin, apply this isometry, this rotation, and then translate it back. So this is what you have to apply. Put G1 is equal to, first apply translation by minus gamma 2 of S naught. Okay, then you apply G, then you apply translation by gamma 2 of S naught. Then this G1 is actually the effective rotation of the Frenet-Serret frame at the point on the curve. Okay, so you see it's like this. You see you have, the situation is like this. You have originally you had this gamma 1. Okay, there is this gamma 1 of S naught. Okay, and at that point you had the Frenet-Serret frame here. Okay, you had this. Then what you are doing is that you are moving this. So there is, mind you, there is another curve. There is this other curve which is the light blue curve like this. This is gamma 2. Okay, then there is this gamma 2 of S naught. Okay, this gamma 2 also has a Frenet-Serret frame which is going to be like this. So it's going to be, oops, this is the Frenet-Serret frame of gamma 2 at S naught. Okay, and so let me use the same notation here also. At this point, this is the Frenet-Serret frame of gamma 1 at S naught. this purple thing, okay. Then this light blue thing is the second curve. At gamma 2 s naught, I have this Frenet-Serret frame here, and I think I have used fs there. So let me also use fs here. Okay. What we have done is that we have moved this red thing by a translation. Okay, so what you do is you have applied this. I have applied this translation. What is a translation? Namely, I am just moving this point to this point by this translation by V naught. So this V naught is just gamma 2 of S naught minus gamma 1 of S naught. Okay, and basically this red curve is translated by this vector, which is the vector that is joining gamma 1 S naught to gamma 2 S naught, right? So what I will get is I will get a parallel curve here like this. Okay. Okay, and this guy is gamma T V naught circle gamma 1. Gamma 1 of S. So let me not put the S there. This is the new curve. Now for this new curve, again there is a Frenet-Serret frame, okay, which is just, see, the Frenet-Serret frame just translates, okay. But you see, when I say for a Frenet-Serret frame translates, I am thinking of the Frenet-Serret frame at every point as if it is sitting at that point. In principle, if you just see it as a frame, it's not, its tail is at the origin. So the Frenet-Serret frame of gamma 1 and the Frenet-Serret frame of T V naught circle gamma 1, they are literally the same. Only thing is they look different because you are seeing them at the points on the curve. Okay, so the moral of the story is here there is one more frame. There is a frame like this. Oops. There is a frame like this, which is so there is one more frame here. And this blue one is a Frenet-Serret frame of T V naught circle gamma 1 at S naught. Okay. Now you see, if you look at these two, this light blue and you look at the dark blue, frames, they are both based at this point gamma 2 S naught. Okay. And if you think for a moment this gamma 2 S naught was the origin, you have two orthonormal right-handed frames, and there is a G which will move this to that. There is a special orthogonal transformation. There is an oriented linear isometry, which is essentially an oriented rotation that will take the, if you want the dark blue, orthonormal frame, Frenet-Serret frame of T V naught circle gamma 1 to the light blue Frenet-Serret frame, which is that of gamma 2 at S naught. Okay, but the point is that rotation is a rotation has to keep the origin fixed, and here you are taking the rotation as in such a way that gamma 2 S naught is fixed. So how will you write it in terms of an actual rotation which fixes the origin? So the point is that what you do the following thing. You apply. So let me write this. So you see, this is what you're doing. What you're doing is you apply translation by minus gamma 2 of S naught. You see, that is this term. When you apply translation by minus gamma 2 of S naught, then what will happen is that I will get at the origin. Okay, so this is the Frenet-Serret frame of this guy. This is the Frenet-Serret frame of T V naught circle gamma 1 at S naught. Okay, it's what I have done is that this gamma 2 S naught is now thought of as the origin, and it's actually having a tail there. Okay, then this light, the Frenet-Serret frame of gamma 2, let us draw it that also side by side. So here you see I have again this light blue thing I have here. Okay, and this thing is the Frenet-Serret frame of gamma 2 at S naught. Now both of these frames are having their tails based at the origin. So there is a G which moves this to that. So the point is here is you have a G here now. You see, there is a G which goes here. So G is an oriented rotation. Okay, that takes the Frenet-Serret frame of TV0 circle gamma 1 to at S0 to for the Frenet-Serret frame of gamma 2 at S0. Okay, now I want to apply that rotation, or I want to apply that frame rotation to the blue curve, which is TV0 circled gamma 1, in such a way that I fix this gamma 2 S0. Only then the Frenet-Serret, the dark blue Frenet-Serret frame of will go and it will get superimposed on the light blue Frenet-Serret frame of gamma 2. You understand? But what is that transformation? So what I have to do is I have to first apply this T minus gamma 2 S0. Okay, then make this rotation G, and then I have to come back by T gamma 2 of S0. Okay, this is the actual see, this is the you see, this is the transformation that will do this job, which will move the Frenet-Serret frame based at that point to another Frenet-Serret, to another orthonormal frame at that point. Okay, so this is my map. Okay, and the point is that there is a translation component here on both sides. Okay, is it clear now? Okay, now the claim is that this if you take this G1, now this G1 is a rotation of this blue curve. Okay, and the claim is that if you apply this G1 rotation, mind you, it's a rotation not about origin, it's rotation about gamma 2 S0 of the blue curve. That rotation, the claim is that it superimposes with gamma 2. It rotates T V0 circle gamma 1 and moves it to gamma 2. That is the statement. Okay, and why that is true is because all of these both of them are solutions to the same Frenet-Serret differential equation with the same initial conditions. Okay, so G1 circle TV0 circle gamma 1s is the same as gamma 2s. Mind you, why is this true? That's because both these curves, both G1 circle TV0 circle gamma 1 and gamma 2, okay, pass through the same point gamma 2 of S0, okay, which is the same, mind you, this is the same as G1 circle TV0 circle gamma 1 of S0, okay, and TV1 circle gamma 1 of S0 is going to be just gamma 2 of S0, okay, and G1 circle gamma 2 S0 is just S0 because G1 fixes gamma 2 S0. Okay, because you look at this expression for if you apply G1 to gamma 2 S0, the first translation minus gamma 2 S0 will take gamma 2 S0 to 0, G will fix 0, and T gamma 2 S0 will move origin back to gamma 2 S0. So you see this G1 fixes gamma 2 of S0. Okay, that is the relative rotation at gamma 2 S0 induced by G at the origin. Right now, so you see these two curves, they pass through the same point, okay, and they have the same Frenet-Serret frame at that point and have the same Frenet-Serret frame at S0. That means both are solutions. So let me first write it like this: both Frenet-Serret frames are solutions of the same Frenet-Serret differential equation. Why the same Frenet-Serret differential equation? Because curvature torsion has not changed. The Frenet-Serret differential equation depends only, the coefficient matrix depends only on the curvature and torsion. Okay, and the curvature and torsion is not going to change because you already taken originally gamma 1 and gamma 2 to have the same curvature and torsion, and you are only applying isometries, direct isometries. Therefore, there are two Frenet-Serret frames for these two curves. They have the same, they satisfy, they are solutions of the same Frenet-Serret differential equation, and they have the same initial conditions, okay, with the same initial condition. What is the initial condition? Passing through the same point and having the same Frenet-Serret frame at S0. Okay, by uniqueness of solutions of differential equations, therefore the frames are the same. Okay, therefore by uniqueness of solutions of first order linear, if you want homogeneous systems of ODE with initial condition, they are the same. See, basically, geometrically the picture is, I have this dark blue curve, which is this TV0 circle gamma 1. Then I have this light blue curve, which is just gamma 2. Okay, and the point is that the dark blue one has the Frenet-Serret frame, and the light blue one also has a Frenet-Serret frame. Both Frenet-Serret frames are based at this common point, which is gamma 2 S0. The idea is that at gamma 2 S0, if you make a rotation to make the frames coincide only at that point, and you apply that rotation to the blue one, it will superimpose with the light blue one. That is the idea. Okay, but how will you write it down physically? So from this blue one, from this dark blue one to the light blue one, there is a rotation. But you see, the rotations are only when you write a rotation, it's only if you want to write it as a rotation matrix around the origin, then you have to only it should fix the origin. Okay, see, rotation, of course, if it's rotation about an axis, it can fix every point in the axis, for example. That can also happen. But what I want to say is, when you want to write rotation as a linear map, okay, then the vector should be based at the origin. So what I'm doing is, you see, this light blue and dark blue frames, they are all based at the origin. So the picture is, when you take the frames, forget the curves. The frames are just three orthonormal vectors, right? So you take the two frames, so you get a dark blue and a light blue frame at the origin. At the origin, there is a rotation. There is a honest rotation, which is a linear isometry, mind you. So call that as G. Okay. Now, what I want you to understand is that rotation, you cannot apply G directly to the blue curve, because that rotation may, the problem with that rotation is that rotation may not even fix gamma, it will not fix gamma 2 S0 in general, unless the axis of that rotation passes through gamma 2 S0. See, I can't take that rotation, directly apply it to the blue curve to get the dark blue curve to get the light blue curve. So how do I interpret it as a rotation about that gamma 2 S0? So basically what you're doing is, a rotation at the origin, how will you make it a rotation at a given point? What you have to do is that you literally go to the origin, make the rotation, and then come back. Okay, that will give a rotation about this point. Okay, which will mimic this rotation at the origin, but now at that point. See, just think about this. See, this is the origin. This is the origin. Okay, this is some point here. I want to rotate by 90 degrees, but I want to rotate about this point. So what I do is I move this here. Okay, that means I translate by the negative of this vector. I make the rotation here. Then I translate it back. That is the effective rotation there. Do you see that? So on the other hand, this 90-degree rotation here, if I directly applied it there, if I did the 90-degree rotation, I will get something like this. I will not fix that point. So if I want to take some rotation here and do it at that point, I'll have to move that point to the origin, apply the rotation, and then go back. Now this rotation, what it will do is that it will take this dark blue curve, it will exactly do this rotation, it will move it to the light blue curve. Okay, and why it does that is because after to the dark blue curve you apply this rotation, the rotation is adjusted in such a way that the Frenet-Serret frame of the dark blue goes to the light Frenet-Serret frame of the light blue curve. Okay, and then the statement is that why is this thing going to superimpose when you apply to the blue curve on the dark blue curve on the light blue curve? That's because both of them will if you write the Frenet-Serret frames, they both satisfy the same differential equation. Okay, because curvature and torsion are the same with the same initial conditions, namely passing through the same point. Okay, and with the same initial same Frenet-Serret frame. Okay, therefore by uniqueness what will happen is that you will get what you will get is that t cap, b cap, n cap for this second curve. So let me write that g1 circle t v naught circle gamma 1 is equal to the same as t cap, b cap, n cap of gamma 2. You will get this, but from this actually you will get gamma 2. This actually is equal to this you will get, because you see t. So let me write this is just one line. You will get g1 circle t v naught circle gamma 1 s t cap. So at s minus g 1 circle t v naught circle gamma 1 of s naught is integral s naught to s g1 circle t v naught circle gamma 1 whole dot ts. Okay, but this is just integral s naught to s. This is t cap. Okay, g1 circle t v naught circle gamma 1 ts, but this t cap is the same as the t cap for gamma 2. Okay, and therefore this is going to be just by the way, remember that this is just d by ds of g1 circle t v naught circle gamma 1. Okay, and this is just d by ds of gamma 2. Okay, and therefore I will just get gamma 2 of s minus gamma 2 of s naught. Okay, therefore you see and I also g1 circle t v naught circle gamma 1 of s naught and gamma 2 s naught are the same. Okay, so they will get cancelled out. So you will get that g1 circle t v naught circle gamma 1 is the same as gamma 2. So this is your m circle gamma 1 is equal to gamma 2, and m is rigid motion. that takes gamma 1 to gamma 2. Okay, do you see that? So see, the point is the Frenet-Serret differential equations are first order in the Frenet-Serret frame, but with respect to the curve they are third order. Okay, because they involve gamma double dot. The curve is gamma. Frenet-Serret frame involves gamma dot, then gamma double dot and gamma triple dot. So they are third order differential equations. But the point is that the Frenet-Serret differential equations, as indirectly, if you write it only in terms of Frenet-Serret frame, it becomes first order linear homogeneous. That is the amazing thing. So it's very easy to deal with. If you look at it with respect to the curve, it's a third order differential equation because it involves a third derivative and it looks somewhat complicated. But the Frenet-Serret differential equation itself being only first order in the Frenet-Serret frame, that's what makes things very easy. Okay. So in fact, without using the uniqueness of differential equations, directly using the Frenet-Serret relations, you can actually write this down. I will do that in the next lecture. Okay.